formulating strategies for battery energy storage systems to bid into electricity markets. So I'm gonna start giving a little bit of an introduction and explain why we care about that. Talk about some of the factors that affect battery cell degradation. Gonna be pretty much just talking about what we've seen on lithium ion, that is the dominant technology, and we're gonna discuss how batteries bid and offer into the electricity market, and then we show some of the results of the bidding scheme we have and of some of the other schemes that some other authors have proposed, and then I'll make some concluding remarks. So in, while we have more renewables penetrating the grids, there is a greater challenge to maintain supply and demand at all times. And especially with PV, we can see that there's the duck curve, and we need fast ramping resources to help balance the grid when the sun is setting or is rising. And also when there's a lot of wind and it's say at nighttime and there's not enough load, we have large units that we do not want to shut down because their startup is expensive or it takes a long time for them to become available again. So storage can make a huge difference in that sense, that it can store that renewable energy when the grid really cannot take any additional energy. So it can prevent renewable energy curtailment. It can help in at times that the load is peaking and the operator needs to bring in some expensive and polluting peaking resources. Storage can simply cover that and prevent the emission from these resources. And also we can prevent startup and shutdown operations. Sometimes the operator thinks that it's necessary to start up a resource just because you need a little bit more margin, and storage can come into play and prevent that startup. And especially batteries, they do not have a startup or a shutdown cost, so they can just make a profit for being available at that time. And for the rest, the grid is good because we didn't have to spend a lot of money and emit a lot of CO2 to start up some unit that might not even be necessary. And so in electricity markets, batteries can profit from arbitrage, right? From buying energy when it's cheap, sometimes even when the price of energy is negative, and selling it when it's expensive, and also provide ancillary services, right? Storage can provide reserves. They have very fast ramping capability, so they can provide frequency regulation, voltage regulation, the ramping products, which you can see as another type of reserves. And one issue with storage is that once you use it, well, you're using your battery and the battery is losing its life, right? There's degradation, or as some authors call it, capacity fade. And when they say capacity in this context, is not the power systems context of capacity being nameplate capacity or rated power, but it's capacity in the sense of storage capacity in megawatt hours. Uh, and Once you use it, it impacts the lifetime of your battery. And sure, your battery wouldn't last forever even if you just kept it unused, but we do need to account for, once we're using it, how much of its life it's you're expending, and how much will it cost for you to replace those batteries in your battery energy storage system later, right? So if you do not take degradation into account, what's going to happen is that every little opportunity that you have to buy energy for say $10 and then sell it at 11, as long as your charging and discharging efficiency are not too low, you will take this opportunity and you will be cycling your battery very, very aggressively, and its life time is going to be reduced drastically. So if you do not take degradation into account, you will, if you're simply trying to maximize the money you make from arbitrage, you will end up cycling your battery in an undesirable way and actually lose more money if you account for how much you're going to have to spend to replace it than how much money you actually made from cycling it. And battery degradation models can be very simple to very complex. And once you start looking into how they came up with those models, you might have questions such as, well, does this really represent what happens when I actually use my battery? Does this represent what happens in daily operations? Typically, these models come from very specific experiments that will not really reflect the operations that a battery will have in power systems, for example. So everything we're talking about here is for lithium-ion technology. It's the most widely used type of battery, especially in power systems. It has a high energy and power density, uh, low self-discharge rate, and its costs have been decreasing uh, very steeply in recent years. Nearly all of the recent projects in the US for grid storage are lithium ion batteries. But the degradation of lithium ion cells that compose those batteries is still a complex phenomenon that's not completely understood. And we know that it's affected. There are several factors, stress factors, that contribute to degradation or capacity fade, and that's battery temperature. And here we have to say that battery temperature is also related to the charge and discharge rate. So it's a bit difficult to include when you're trying to solve a problem to determine how you're going to use your battery to bid or to offer into an electricity market, that you'll be able to tell how much your charge and discharge rate will affect the battery temperature. You need a model of how does the cooling system work, and how does that charge and discharge rate affect the battery temperature. So even though we have these two factors over there, they're very well connected and difficult to separate. And the main factor from our perspective is the depth of discharge. So um, once we have a battery, say that's charged to 90%, and then we're gonna sell that energy. And sure, we will not violate the specifications from the manufacturer that says that we cannot go below, say, 15% of the state of charge. Um, but if you're every day cycling your battery uh, in a range of like 80% of its capacity, even though that's within the specifications, its life, its useful life will decrease very quickly. If you're instead doing discharge cycles that have half of this depth, then the battery will degrade much more slowly. And some batteries, so lithium ion technology has many different chemistries, but some of them, the manufacturers say that you should try to keep them, their state of charge when not being used, within sometimes 50% or sometimes as low as possible within the range. So this is also something that we can account when we're thinking about degradation for these batteries. And also just the battery age itself. You're keeping the battery even at a certain say ambient temperature, 25 Celsius, you're still losing a bit of its capacity every day. And so most of these degradation models come from accelerated aging experiments. So uh, some researchers will get a few batteries, or maybe many batteries if they can, and put them in controlled temperature rooms, and be cycling them in a systematic way, um, non-stop, so they can try to predict how will the battery behave in 15 years without having to wait those 15 years, right? So these experiments are very expensive, time intensive, and since they're always cycling the battery the same way, or unless they're really designed to for a very specific application where they can actually simulate how the battery would be used, these experiments may not really be appropriate to say how your battery is going to degrade once you're just using according to certain price profiles in say the California grid or the New York grid. So it can be very challenging to find a model that will fit the application for your battery. And so once you start looking into the degradation models that are out there, you might see um, some researchers finding some very detailed models where they're fitting a bunch of coefficients, making many assumptions, and going into a very high level of detail. But in the end, you end up using information that you don't really even have, and it might be better just to use a simpler model that will account for degradation in a more general way. And that's the approach that we've been using here. So our main concern is with the depth of discharge. And so here, so many batteries have a specified number of cycles that it will be able to perform during its life. And if you do, say, a cycle at 80% depth, then you lose around 0.03% of those number of cycles that were specified. And so this is a curve for a certain type of lithium ion battery. And what we do here is that we consider a replacement cost. So if you have a battery um, and you paid some amount of dollars per megawatt hour of storage, then you can see that once you lose a certain percentage of your life, you're going to have to spend that money again. And so we just take this amount of cycle life lost and multiply by this replacement cost. Um, so this is the main thrust of the degradation model that we use. Um, we find a way to, when solving the dispatch problem, the scheduling problem for a storage resource, to account for the cycle depth. Uh, we do this by breaking down the energy that's stored in the battery into different bins, each one corresponding to a certain depth. And so once we are taking power from a certain bin, we're keeping track of how deep we are in this stack, and then making sure that we're accounting for the certain amount of life lost.
So I'm not understanding this slide very well. So let's assume I'm at 60% cycle depth. Then I read the figure there, say it's 0.02,
Oh.
okay? And that means that it loses 2/100ths of its life.
0.02, right?
Yeah,
What?
0.002. Okay, you said it's percent.
Yes, yes.
So it's 2/100ths of 1%.
Yes.
Okay, what is that? That's what I'm trying to ask you. Is that for every cycle? That's what I don't understand. What this is illustrating.
Yes, for every time you cycle it at 60% depth. So if you range from some value to that value minus 60 and go back, this is the impact. You lost 0.02% of your cycle life.
Per cycle.
Yes.
Okay, so let's assume this battery has 1,000 cycles, right?
Okay.
Okay, and we're going to take 2 over what? 2 over 10,000, right?
Yeah.
That's what the loss is. So are you telling me that by the end of that 1,000 cycle, it has lost 20% of the SOC? That I understand, but this is where I get into trouble with the cycle of depth.
No, so this means that after you've done all those cycles, you've spent, say, so the manufacturer told you how many cycles you should expect to get from that
Yeah,
battery.
yeah, let's assume it's 1,000 is a lifetime. At that point, it drops to 0.08 SOC. That's what it means.
No, I mean, we're not really looking at how the SOC drops here. It does
I
drop.
understand, but the cycle depth or SOC, the two are complementary, you know?
Yes, yes, they are. And so what happens? Let's forget about this graph for a moment, right? So you have a battery, and you say you use it once a day, you cycle it every day, right? So as you use it, the capacity, the storage capacity in energy units starts to decrease continuously, right? Slowly, and this is accounting, this is trying to account for that, saying that, oh, if you keep doing cycles at this much, you're gonna lose this number of cycles. And to find like this number of cycles that the battery can do throughout its life, they set a threshold that, oh, once the battery's capacity, the maximum SOC, is only say 80% of the nominal of the one that it had when it left the factory, then that battery is done. Um, it reached the end of its life.
Well,
So
that's what I'm trying to have you interpret for me.
yeah,
And I'm
so
not getting it from this slide. I'm not understanding the how to read the slide correctly then.
so what we're saying here is that they gave you a number of cycles, so say 1,000, right? So every time you do a cycle of a certain depth, you're gonna take that number and multiply by the y value here, and you see how many cycles you lost. But it's gonna be a number. It might be less than one if
So
it was
I'm
a shell.
making a situation easier for you. I'm saying, let's assume we bought a battery which has 1,000 cycles. We're going to run 1,000 cycles, and every time I go to a cycle depth of 60%. So after
Hmm.
1,000 cycles, I'm going to have I'm going to lose essentially zero point zero 0.02 times 1,000, right? Which is 20%.
Hmm. Yes. So you
And that
lost.
means that that's the end of life of that battery, right?
I- So it depends. I mean, you said that the battery had what, 1,000 cycles, correct?
I'm making it very simple example. That's I'm trying to understand this
So
curve.
so the way the manufacturer says, it's usually something like, for example, this battery, I think it has 3,000 cycles at 80% depth. Um, so let's think about the numbers that these numbers. So once you've done 2,000 cycles at 80% depth, you're gonna have already you already spend those 2,000, and you have 1,000 more cycles at this depth. But if you're working with, say, 50 or 40% depth, we can see that the life loss is half. So you have the double number of cycles left. And this is all an approximation, right? Because in the end, you might have your battery with 80% capacity, and it's still working. It has a bit more of impedance, but it's still fine. So this is it ends up being an approximation for you to see how much how much you're hurting your battery when you use it. Um, yeah, I don't know if I managed to answer your question, Professor.
Well, it would have been good to have a slide like that, which would show that.
And so the cycle depth is the main stress factor for batteries, but temperature is also very important. But it also depends on how the system operates. So you can have an installation where there is some cooling for the batteries, and then temperature may not be such a determining factor. Um, and so, along with battery temperature, that can be actually a bit hard to represent in a linear program, which is what we use to design the bids and offers for a battery. There's also some batteries that degrade more if they stay in a certain SOC value or away from say 50% or 40% SOC. Um, and so representing this cost of being uh, away from an ideal SOC is easy to do in a linear program. But again, this is information that it's difficult to find for a specific battery. And we might be changing our model into something very detailed when we don't even have the capability to represent those coefficients, the parameters that we would need to actually make it accurate. And the charge and discharge rate is also, it's very straightforward to put in the linear program, but again, it's very connected to the battery temperature, right? A lot of the degradation that is associated with the temperature is coming because the charge and discharge rate affected the temperature. And so you try to make a detailed model, but you're still separating things that are connected and ending up with something very complex that might not be uh, as good as something that's simple and will try to prevent you from overusing your battery. So in this work, we're only accounting for depth of discharge, and we think that we can represent these additional factors. And if we had this kind of information from the manufacturer, this would be straightforward to add to the problem. And so uh, FERC order number 841 established that operators must enable storage resources of 100 kilowatts or more to participate in electricity markets, and they should be able to set prices by submitting bids and offers, or they can also self-schedule. So in both cases, either when the battery owner is submitting bids and offers or is submitting a dispatch schedule, they do that using price forecasts. So they have either a single price forecast for each hour of the next day, or they have a distribution for a probability distribution for each hour of the day, and they use that information to decide either their offers or their schedule. And many papers that deal with batteries in electricity markets just assume that those battery owners are going to submit a bid offer of a single block, which is pretty much the same as submitting your dispatch schedule if that offer is like very low, at a very low price, and if the bid is at a very high willingness to pay. And so this might make sense if you have very accurate price forecasts and you trust it so much that you're just gonna use them and decide the schedule to maximize your profit. But in reality, uh, we know that especially once you have more renewables into the grid, it makes more sense to account for the uncertainty that the wind might be blowing, that maybe there will be cloud covers. And so, from a battery owner perspective, you might not be that interested in simply submitting saying, oh, I'm going to charge at this time no matter what. It might be better to say, no, I'm going to charge here given that the price is low enough, and actually submit an offer curve that you buy more energy if the if the energy is sorry, an offer curve, you sell more energy if it's more expensive, you sell less energy if it's cheaper. And as a bid curve, right, you buy more energy if it's cheap, and you buy less energy if it's expensive. And so the way we formulated this bidding problem is that we put uh, variables to describe each of the blocks in the bid and offer curves in that a battery energy storage system submits to the market. And we also explicitly represent the price uncertainty by taking sample paths. So we take a possible price profile for the day. So 24 hourly values of prices for the day. Well, we can take like 10 possible profiles for the day. And so our goal is to maximize our profits. And by profits, I'm saying that we're trying to maximize our revenue for selling energy, and we're also taking into account how much money we're spending to charge to so the how much money we spend, our costs to get the energy to charge, and also taking into account the degradation costs to our battery, thinking that keeping in mind that eventually we're going to have to replace that system, and if we use it too aggressively, then we will have to replace it rather sooner. So the results we present here are for a small 20 megawatt battery energy storage system that has 12.5 megawatt hours of storage capability. We consider an efficiency of 95%, and the battery replacement cost is $300,000 per megawatt hour. The depth of discharge, sorry, the degradation uh, due to cycle depth is that from the slide before where we were discussing. And I took LMPs, right, electricity prices from a node in San Jose in California, and here we consider four prices. So 4 weeks of prices, hourly prices of electricity at that node. And this is what happens when we take this battery and we forget about degradation, and we just say we want to make the most money possible. I don't care about if the battery is over after this week. We're just gonna use it as much as we can. And so you can see uh, that the battery is cycling multiple times per day, and in the last day it cycles many times. And for this case, the profit from just selling and buying energy, so it was $5.2 thousand for this week. And this is on average, right? Assuming that the prices will be like that, these four prices, we're taking the average of this. And the degradation cost when we use the battery like this was around $2.7 thousand. And so our overall profit when we take degradation into account was actually 2.5.
Wait, I don't understand your Lance curve.
The start
How can it the stored energy go from 12 megawatt hours to 2 megawatt hours in no time at all?
Well, so this is a sampled system, right? So once we've used, um, you can see the net injection in the middle. It is instantaneous. Once the net injection is that, then the stored energy at the end of that hour is shown in the graph.
Well, what you have is instantaneous change of energy at the point of time.
Yes, because it's all a sampled system, right, Professor? We're
Right.
not showing the
But
energy.
the energy can we know that it has a capacity of 20 megawatts. to change it. So it would be over the hour duration for it to go from the energy which you show to the energy it goes down to or it goes up to. It doesn't happen instantaneously the way you draw it.
So I mean, this is all. These are all values for 1 hour, right? Sampled for 1 hour. Um,
Yes, but I'm trying to tell you that in an hour you have this drop from 12 to 2 instantaneously, and it can't happen that way.
so in that hour, we were using 10 megawatts. We were injecting 10 megawatts. So from that hour to the next, it jumped 10 megawatt hours. And we're not showing it continuously. I agree with you. We're not showing the ramp.
It's doesn't seem to be very meaningful the way I look at it.
What we're showing here is one single value for each quantity, at least for the bottom. The other one has four values, but one value at each hour. We're not showing how the energy goes from one to the other. I'm not showing that slope.
Well, that's why but you're showing it, Adriano, you're showing it as a curve and you're showing it continuously. And what I'm trying to tell you, if you would, if they were not connected, the top point to the bottom point or the bottom point to the top point, I can use my imagination. But what you're showing is an instantaneous decrease or increase in energy level.
Mhm. I see your point. I should have used a different style for this plot. I'm sorry. Um, yeah. So the main point here was to show that we are cycling this resource very aggressively, especially in the last day. And the next slide, we take into account degradation. So when we're solving the problem now, we say, okay, I want to make the most money out of this, but I'm also accounting for the money that I will have to spend to replace the battery. So we're taking the degradation cost into account. And you can see that now the cycling is much less aggressive than before. And in this case, our profit from arbitrage, from buying and selling energy, is a little bit smaller. Now we're talking about $4.9 thousand, but the degradation cost is much smaller. Is $1,000, $1,100. So our overall profit now is much higher. Is $3,700. But what's going on here, when we're computing our schedule here, we're using the self schedule or the single energy block bid and offer curve. So what happens here is that for each of these, for each hour, there are four possible price values. And what we're going to do is we're going to decide uh, how much energy we're buying, selling, or if we're not doing any of these. And in the next slide, what we do is we actually submit curves for offers and bids, so that depending on the price of energy, we're going to be selling more or less and buying more or less. So you can see that the behavior is perhaps a bit less aggressive than the previous one, but this is really uh, just a, it's not, the degradation model is still the same over here. And now our profits from energy are higher than before. We're very close to $5,000. The degradation costs are lower than before, very close to $1,000. And so the overall profits is $4,000. And so in this case, even though we're showing a certain net injection profile and a certain stored energy profile, it would depend on what price actually gets realized to see how the storage resource gets cleared in the market to decide how this net injection and stored energy profile would be. Um, but at least for these four prices, and so if you consider that you have a good estimate of the price distribution, you can say that on average you are maximizing your profit and you're taking into account the degradation costs that you have to incur, say in a few years once you have to replace your battery. um, and so this is the last result that I had, and this is my presentation. If anyone has any questions, I'll be happy to discuss.
So in this last graph, you show 15-minute intervals, right, for the net injection or withdrawal.
No, it's everything is 1 hour.
But what was that 15-minute interval stuff that you were talking about that?
I'm not sure. 15 minutes.
I thought you said 15-minute intervals.
These are all 1 hour.
They're all 1 hours. So just somehow, Adriano, when you have a withdrawal there, and corresponding to that, there's no change in the energy. I'm not seeing what you're displaying.
Can you show me where that happens, Professor? I'm sorry.
I'll take, for example, the second high value of the 12 in the bottom graph, the second one.
Here.
Oh, yes. So
So
above it, there's a big withdrawal there for an hour.
so this is net injection, right? So we were charged, and then we injected energy into the grid, and we lost the energy.
No. I'm talking about the net injection, which is negative above it.
This one.
Yes.
So we didn't have any energy, and then we drew energy from the grid, and now we're charged.
But you don't have a different value from the start to the finish. That's what I'm saying, that you still have a flat value.
Are you talking about the fact that it changes suddenly from not being charged to being charged?
No, I'm talking about the fact that in that long period where you have the high level of storage at 12, it doesn't reflect the fact that you depleted it to -10 for that entire hour. So that means that there should be a corresponding reduction in the amount of stored energy.
I mean, so we started here right at 5, and we drew some from the grid. We came up here, and then we stayed
I
still.
understand that. I'm just saying for that, whenever there is that long stuff, I don't see the change. That's all I'm indicating. It doesn't seem, I mean, that has to be some kind of integral of what happens when you do that injection or withdrawal action. And I don't see a corresponding change in terms of the energy stored.
Okay, I think that it's probably because of my poor choice of style here, but I've checked this. I mean, this particular injection here, it's lasting for 2 hours. So for 1 hour it was around, say, 3 megawatts, and then it went to 6 or 7, and so this is how it depleted the energy over here. Um, I mean the
But after that, you have that long one, which goes down till -10. And
Yes.
below it, I don't see any change in the storage.
Oh, the
When
storage.
for 1 hour, you have a minus 10 change from 0,
Yeah, I
and
mean,
the storage still remains fixed.
no, the storage was depleted, right? It was at the minimum over here, and once we withdrew, we came back up to 12.
Adriano, I'm talking directly above the from our I guess it's 12, where you have all those small changes, but
Mm.
then you have a big depletion over here, and corresponding to that, my energy stays constant unless I don't know how to align those scales.
Yeah, I think it's my bad choice of style here, Professor. Um, it's it's just I'm gonna make sure to plot this better next time. It's not wrong, but the graph is not helping. I understand.
Okay.
So, unless anyone has any questions, I think that I can end the presentation.
Any questions? Any announcements? Any discussion? Okay, I think we can end it.
All right. Thanks, everyone.